Hi everyone, in this Connect with Networking video, we're going to continue our discussion of Chapter 3, the physical layer of the network stack. Let's go ahead and get started. In the first half of this chapter, we discussed the various means of sending a signal, either using guided media or radiated media. Once we've determined what media we want to use for our network, the next thing we need to figure out is how to actually send a signal along one of those medias. What we're looking for when we're sending digital information is a simple set of zeros and ones. The only thing a computer understands is an on switch or an off switch, or zeros and ones, binary. And we can do that pretty easily using electrical signals. But if we are transmitting using something like a phone line, those networks have been designed to broadcast sound waves, which are analog, and they are continuous waves with curves and ups and downs that do not necessarily lend themselves as easily to digital transmission. So we'll talk a little bit about how we solve that issue later in this chapter. Another thing we have to deal with when transmitting information is that we are often trying to translate from something we understand as human beings to something a computer understands. Computer only understands on and off, 0 and 1. If we want to represent something like letters in the alphabet, or symbols, or even digits that you would type on a keyboard, we need to come up with some sort of coding scheme. And one that we've used for a very long time is ASCII. Computer scientists came up with a series of zeros and ones that represent a particular keystroke on your keyboard. So if I want to type capital letter A, what I would then broadcast across a network is 01000001. This is a specific number in binary, and it represents capital letter A. All the different keys on your keyboard are represented with a specific ASCII code in binary. Modern networks often use something like UTF, which is an extension of ASCII, and allows for many additional symbols above and beyond what you might see in a normal keyboard. Also allows for symbols you might see in other languages. But the idea is still the same. We take the various symbols that we use to communicate as human beings, and we represent them as a series of zeros and ones that a computer can understand. When we're transmitting digital data across a digital network, we have a couple of choices of transmission modes. One would be a parallel transmission, and this is where multiple bits are transmitted at the exact same time. If I wanted to send 8 zeros and ones, or a byte of information, which could represent a character on your keyboard using ASCII, I could send all 8 of those bits across a specific transmission media at the exact same time. This is an efficient way of sending information, but there are some coordination concerns. If the synchronization of these 8 bits gets off in any way. For instance, if a cable was bent as it transmitted across a larger distance, a few meters or a few hundred meters, things could get out of sync. You might be receiving the zeros and ones at the top of this set of 8 earlier than the remaining 6 zeros and ones, and as a consequence, you might be confused as to what message you're actually receiving. So there is a synchronization issue. We typically see parallel transmission used for short distances. Things that are inside your computer, like your CPU communicating with memory, almost always uses parallel transmission. The distances are tiny, and so we don't have to worry as much about synchronization. And it's a very efficient way of sending lots of information at one time. When we start to increase the distance, things like a network, where we are broadcasting across meters or kilometers or hundreds of kilometers, parallel transmission is not as common. Instead, what we would typically adopt is serial transmission. This is where we're sending bits one after another sequentially along the same narrow path. There's no need to worry about synchronization. You're receiving every single bit one at a time. This does mean that the pathway is narrower, and the only way to speed up transmission is to send more bits in a short period of time. So it does limit the amount of bandwidth that is available, but we've found that with various techniques and technologies, we can send a vast amount of information across a serial transmission channel. All of you have used serial transmission on your computers for your entire lives. You've plugged in things like mice and keyboards to a rectangular plug that is called a USB port. You probably haven't given it much thought, but USB stands for Universal Serial Bus. Bus is a fancy term in computer language for a pathway. Serial means the information is being broadcast one bit after another, and universal means we have a common plug for all of our various devices. So Universal Serial Bus is using serial transmission to send information to and from your mice, your keyboards, and your other peripherals. Before we actually set up our network, we have to have a common standard for what represents a 0 and what represents a 1 on our network. For instance, maybe we decide that positive 5 volts across an electrical wire represents a 1, and 0 volts represents a 0. Once we decide on the set of symbols, we then can figure out what kind of symbol rate we can represent. On a serial channel, the rate is simply going to be how many symbols we can send over a period of time. On a parallel channel, we are going to be multiplying that by 8 or 16 or 32 because we're sending multiple symbols at the exact same time. Old school phone lines would broadcast at around 64 kilohertz, which was around 64,000 symbols in a single second. One of the simplest ways of representing digital data would be unipolar, where 0 voltage is a 0 and positive voltage is a 1. If we want to send a series of zeros and ones, we would send 0 volts of electrical signal for a specific amount of time to represent a 0, and 5 volts of positive electrical signal for a specific amount of time to represent a 1. The issue with this unipolar signaling is there's no way to differentiate between a 0 and no signal. It's hard to tell if the lights are off or the lights are off because you're sending a 0. So it's challenging to actually differentiate between we're not talking or we're talking, but we're sending you a bunch of zeros. So this is not a particularly popular way of sending digital information today. Alternatively, we could add negative voltages to the positive voltage model to get better differentiation. Because the minus 5 volts and the positive 5 volts are farther away from each other, it's much easier to see a 0 versus a 1. And additionally, when you stop broadcasting, there's no electrical signal, so it drops to 0 volts, which is actually a third symbol, if you think about it. Minus 5 volts is one symbol, positive 5 volts is another symbol, and 0 volts is a third symbol, which is, I'm not saying anything. So there's an advantage to adding both positive and negative voltages. This is called bipolar, non-return to 0. One of the challenges for both of these techniques is it is difficult to see the difference between 2 or 3 or 4 symbols being sent sequentially. Seeing the difference between 2 zeros and 3 zeros is hard because there's no additional information other than a long stretch of time where you are sending the same voltage. A way of improving that signaling would be to add return to 0. This slide has an example of bipolar return to 0, where every 0 is sent using minus 5 volts, but between each 0 that's being sent, we let the voltage return to 0. Each 1 is sent using positive 5 volts, and then we return to 0 between each 1. So unlike the past picture where 3 zeros in a row was just a long stretch of minus 5 volts, in this case it's 5 short pulses of minus 5 volts to represent each of the zeros. This makes each of the individual signals much easier to differentiate. There is a fourth type of signaling called bipolar AMI. I'm not going to talk about this, and you are not responsible for knowing it. But you are responsible for this fifth type of digital transmission because this is the transmission technique that is used in modern networks. When we talk about Ethernet, which we'll be talking about in the next chapter, it uses Manchester encoding to send either zeros or ones. And unlike the other models, the top position or the bottom position doesn't represent a 0 or a 1. A 0 or a 1 is represented by the movement from positive to negative voltage or from negative voltage to positive voltage. This is easier seen if we add some vertical lines to this picture. If we look at the bottom of the next slide, you can see that Manchester encoding represents a 0 by letting the voltage drop from positive 2 volts to minus 2 volts. The very first part of this time segment is the drop from positive to negative. That represents the 0. And in the second time slot, you can see a drop from positive voltage to negative voltage to represent a 0. And in our third 0, you can see that it starts at positive voltage and drops to negative voltage. For ones, we start at negative voltage and rise to positive voltage. So the third digit that we're sending, you start at negative 2 volts and you increase to positive 2 volts. The fourth one we're sending, we start at minus 2 volts and we rise to positive 2 volts to represent a 1. Zeros and ones are represented by movement from negative to positive or from positive to negative. That does mean that in certain time periods, you'll see two movements. The first movement is the information that you're sending. The second movement is to prepare for the next time segment. So we look at the very beginning here where we have 2 zeros in a row. You see the first movement is a drop from positive 2 to minus 2. The second movement is back up to positive voltage. That doesn't actually signal anything. It is preparing for the next 0 in the next time slot. If we look later on in this segment, we have 3 zeros in a row. We drop from positive to negative to represent the first 0. Then we rise in anticipation of the next 0. We drop from positive to negative for the second 0. Then we rise in anticipation of the third 0. And then we drop from positive to negative for the third 0. Then we stay at the bottom because the next digit we're about to send is a 1. And we cross over into the next period and then rise to represent that 1. If you see two movements in a particular time period, it means you're sending two of the same thing in a row. You're going to send a 0 and then send another 0, or you're sending a 1 and then you're sending another 1. So while that second movement doesn't actually represent anything per se, it does give you a clue as to what's coming up next. You can anticipate what's going to happen. If you dropped from positive to negative voltage, you're receiving a 0. If you then saw the rise from negative voltage to positive voltage, you're anticipating a 0 for the next data point. And when it does fall from positive to negative, it just confirms what you were expecting. So while that second piece of information doesn't technically represent anything, could you use it to actually check your work? You sure could. And it turns out that Manchester encoding, because of the way it's using these rises and falls from positive voltage to negative voltage, is extremely effective at clearly signaling zeros and ones so well that it actually uses lower voltage. If you look at this entire picture, all of the other models use positive 5 or negative 5 volts, but Manchester is at lower power, plus or minus 2 volts. This is a very effective way of sending information using very little power, which is why it's been so widely adopted in the modern internet model. Sometimes we don't have an electrical network to send our digital data, and we have to rely on old school analog networks. The telephone system was not designed for digital data. It was designed for analog data. It was designed to take voice waves, convert them to electrical waves, and then send those electrical waves as curves, and then on the other end, retranslate from the electrical waves back to analog. So while it does use electricity, it was not designed for digital data. In order to make this translation from voice to electrical and back to voice, you need a modem. Modem stands for modulator demodulator. You modulate the signal from an analog audio signal to a digital electrical signal. You broadcast that signal, and then you demodulate the electrical signal back to an audio signal. A modem modulates and then demodulates. If you were asked what a modem stands for and you only said modulate or only said demodulate, you wouldn't receive credit. So make sure you are recognizing that it does two things. It modulates and then demodulates. When we are sending electrical waves across a network, there are 3 characteristics of waves that we can use to represent digital data. We can use the height or amplitude of the waves, which would correspond to the volume of an audio signal. We could use the frequency or the number of waves that are happening in a time period, which corresponds to the note you would be playing on a keyboard or a guitar. Higher notes are higher frequencies and more waves in a given period of time. Or you could look at phase, the direction the wave is moving at a particular moment in time. A carrier wave is how we are sending a wave across a circuit. We modulate that wave to send either more waves, increase the frequency, less waves, decrease the frequency, louder or softer, increase or decrease the amplitude, or reflective to change the direction, modulation of the phase. This would be called amplitude modulation or frequency modulation or phase modulation. And it turns out for digital broadcast, we use a combination of these different techniques to send information. If we were to use just one of these techniques at a time, we would do something like a short wave representing a 0 and a tall wave representing a 1. So quiet noise represents a 0 and loud noise represents a 1. Or if we wanted to use frequency modulation, a low note represents a 0 and a high note represents a 1. Or if we wanted to use phase modulation, a wave that starts a certain time period moving downwards represents a 0, a wave that starts moving upwards represents a 1. I think this third one, phase modulation, is the more difficult one for us as human beings to interpret, but it turns out that electrical equipment can recognize phase modulation very easily. By using different frequencies or amplitudes or phases, we can represent more than one symbol at a time. If we just use quiet notes or loud notes for zeros and ones, we can represent one symbol. We can use those two symbols to represent one bit of information, 0 or 1. If we had 4 different volumes, soft, medium, medium-high, and high, those 4 symbols could represent 2 zeros and ones. A 0, 0 would be the softest note. A 0, 1 would be a slightly louder note. A 1, 0 would be an even louder note, and a 1, 1 would be the loudest note. If we did something similar with frequency, 4 different notes that you strum on a guitar could represent the combination of 0, 0, 0, 1, 1, 0, or 1, 1. If you wanted to represent 3 zeros or ones in a row, you'd need 8 different symbols to represent 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Those are 8 different combinations of 3 zeros or ones. So you need 8 different notes or symbols to represent 3 bits. Every time you want to increase a number of bits, you'd have to increase the number of symbols 2 to the nth power. So here's an example of 2-bit amplitude modulation where we use 4 different heights of the wave to represent 2 different combinations of bits. You can see 0, 0 is the shortest waves, 1, 1 is the tallest waves, 0, 1 is slightly taller than 0, 0, and 1, 0 is slightly shorter than 1, 1. 4 different heights. As you increase the number of symbols that you need for bits, the differentiation becomes more and more difficult. Many of you that are musicians know that hearing the difference between C and a C sharp might be really challenging because those notes are close together. And similarly, as we increase the number of measurements we need to take for these waves, telling the difference between a 1, 0 and a 1, 1 might become really hard. Modern networks have combined different types of modulation to come up with higher bit rate. One of the most common modulation techniques is called quadrature amplitude modulation. And for instance, we used to use something called 16 QAM on our phone networks. And this would allow for 8 different phase shifts or different directions of the wave and 2 different amplitude levels. And by combining those 8 different phase shifts and 2 different amplitudes, we had 16 possible symbols, which allowed us to send 4 bits in a single symbol. So 4 zeros and ones strung together using 8 different directions of the wave and 2 different volumes of the wave. Modern networks use advanced versions of quadrature amplitude modulation. Many cellular networks, for instance, now use 64 QAM, which is 64 different symbols using a combination of phase and amplitude to represent 8 bits per symbol. And here's an animation that represents some of the various ways that we could send a combination of zeros and ones. So you can see at the top of the chart, if the amplitude was at 25% and the phase was at 225 degrees, that represents 1100. If you change either the amplitude or the phase, you could represent a different combination of 4 zeros and ones. Sometimes we're trying to actually translate digital information into analog data. If you're ever listening to music on your computer or your phone, that music is stored as digital information, zeros and ones, but you want to hear it as a curvy, smooth analog wave. We do so using what's called a codec, which is the opposite of a modem. We codify analog information as digital, and then we decode the digital information to analog. So we're doing the opposite of what a modem does. One way of doing this would be to use pulse code modulation. PCM samples an analog signal at regular intervals. It then measures something like the amplitude of each sample, and it quantizes that amplitude as a series of zeros and ones. Anytime we do this, we are approximating a smooth analog curve, and as a consequence, there will be some loss. But we can get to the point where the loss is imperceptible to human perception. So if we wanted to use a digital network to represent an analog voice call, we could take the analog curve of someone's voice, we could codify it as zeros and ones, send those zeros and ones, and then on the other end, decodify the zeros and ones back to a curve. You can see that what we're doing here is we're measuring the curve at different equal periods of time, which would be moving across the x-axis. And then we're measuring the height of the curve at any moment in time to estimate how high that is using a series of zeros and ones. If you want this to sound better, you would either measure more frequently, so the time frame would get narrower, or you would measure more precisely the height of the wave, so the number of zeros and ones would get higher. And if you've ever looked into music, you know that it often is represented by its kilobits per second. Old music used to use things like 64 kilobits per second. Modern music is often 320 kilobits per second. And that's a representation of how frequently you are measuring the wave. So how many times in the x-axis you're actually looking at the height of the wave. And the other thing you know is that music is represented using bit rate. And most modern music is using things like 10-bit or 12-bit measurements. So that's how precisely we are measuring the height of the wave, is instead of having 3 bits like we have in this picture, we have 10 or 12 or 16 bits of precision for the height of the wave. And by combining a more precise wave height and a more frequent measurement of that wave height, we can get very precise representations of analog information as digital signal. To wrap up this chapter, some things that management might want to walk away with. If you are broadcasting digital data, you should use a digital network. Digital cabling is very inexpensive, very reliable, and does a great job of moving the zeros and ones from one place to another. As networks progress, we're seeing less and less use of old school voice networks, and voice networks are being replaced or supplanted by data networks, even for analog communications like having a phone call. We should also acknowledge as managers that wired networks still remain more secure and reliable than wireless networks. So while wireless certainly is convenient, it is not without its risks. That's it for this chapter. Thanks so much for watching and listening. See you next time.